Hey, my name is Michael. I've been a big follower of yours, all of you watching. If you're involved in the natural law project in reforming the sciences, I'm glued to my seat, listening to what's going on between Kurt and Dr. Brad. And what I want to do is I want to talk today about this, basically this idea of the triangle where Kurt has the negentropy positive arrow up top. You see that little brown drawing at the top, and the E minus, or the entropy direction, towards the bottom. I want to talk about that today. And just to introduce myself, like I'm a high school tutor and college tutor of mathematics, but also really all subjects. Any subject with an existing textbook, I'm typically years ahead of even the best students in high school and college in terms of the breadth and depth of knowledge and practice that I've had with those subjects. I'm sort of a self-taught academic jack of all trades, master of none. But I essentially, because I've mastered the art of like self-teaching academics, basically, I have the ability to empathize very highly with my students who are also having to plow ahead on their own and try to self-teach. So I know how to model self-teaching and modeling. That's what my job has basically become. And that's what being a good math teacher is that the students see you modeling something in real time. So I'm going to talk about this triangular model that Kurt has talked about, and I'll just give you my understanding of it, because my understanding may not be completely accurate in the end, but I think this is an excellent model to see that's going to be very diagram rich, and it's going to connect a lot of different concepts and subjects you've probably been exposed to. So with that, let's begin. All right, so I threw up on this whiteboard here the definition of entropy. So this is the generalized definition of entropy. And I'll beg your pardon, I got to be reading from my notes because I got about 8 pages here. So I'm just going to try to go fast through them all. What I recommend, by the way, is that you grab some coffee. I have some for me, and grab a notepad and write this all down. Write down what's on these screens and go over it later, because I'm going to try to go fast through it. So the entropy, okay, is the number of multiple choice questions needed to know what something is. Now, when I say multiple choice question, the most common version of this is we do true false questions. And when you ask the questions just in terms of, are you this, or are you this, true or false? And you just design the tests to record an answer of true versus false. This is what's called the Shannon entropy. And just so you understand, if you're looking at an object and you want to classify, classifying an object in physics involves all these different things, right? So you've got you've got an object's mass. Let's say you've got its position vector, you've got its velocity vector. In fact, you have an infinite number of, or a seemingly unending number of, differentials that you can take. And so you've got acceleration, you've got jerk, which is the third derivative, third order term, and you can just keep going fourth order up to some value that you want to do, an nth order, right? And this is what's called the Taylor series, and also something known as the exponential, which I can get into in another video. But essentially, you're gonna need a bunch of different true-false questions just to ascertain the mass, right? And then to ascertain the position, and then to ascertain the velocity. So the sum of the entropy, or the number of true-false questions that we need to answer to get each of these individually, we can add those up together to get the unique intersection, the unique object that satisfies, in set theory, the intersection of all of those different properties. Now, you also have things like not just mass, and you have things like temperature, right? You also might have, for instance, like all these different energy values, right? Like what kind of light energy is reflecting off of it, how much heat, right? Itself, the object is holding. These are all things that you might want to know. Even other things like density. density in in a region of that object. So wanting to know the answer to all of these things, you're going to have to ask more true or false questions, but it's logical to assume that you can just add the question, you can solve each problem additively. I think the better definition for us is really to look at it in terms of it's the number of steps needed to disambiguate an element of set X. And if we do it in the Shannon entropy method, we get a formula, which is that the entropy up to size X is basically the log base 2 of the set size. I'll just do it this way. The entropy of a set size is going to equal the log, which I'll just say base 2 of the set size. Sorry, I can't write it any better, and I'll try to handwrite it. Actually, gosh, getting good with Zoom is always a chore. Yeah. So the entropy, up to size X. If you like the chalkboard math way of thinking about it, it's just the log base 2 of X, where X is equal to the size of the set. Okay. So if you have a set with, and I'll demonstrate this on the next whiteboard. So if you have a set with 10 elements, or sorry, if you have a set with 8 elements, so I'll give you an example. Suppose you have a set with 8 elements. The Shannon entropy, E, sub n, let's just say, E sub 8 is going to equal, and I'll just handwrite it out, the log base 2 of 8. And anyone who knows their algebra, high school math, or whatever knows that's 3, because you read that statement, the exponent that turns 2 into 8 is 3. So that's the way to kind of think about it, is that it's a map that sends 2 into 8, and we call that map the number 3. And of course, the process is powering, right? Raising it to a power that the arrow symbolizes. And so the Shannon entropy would be 3. And why is that true that you need 3 true-false questions? Well, let's just suppose we have the 8 elements, and I'll just rank them in an ordinal measure. So I have, again, we're assuming that we have the elements listed in an ordinal fashion. So we're excluding the work that it took to actually do the counting of the elements, let's just say, and getting the set size itself. But once you have the set size, look at this, it's called the bubble sort algorithm. So basically, you can ask the question, are you greater than or less than 4.5? Which, by the way, is a calculation you can get algorithmically. It's called the median of the set. So if you perform that test, you've now limited the numbers to greater than or less than, basically the median. Over here, it's greater than. Over there, it's less than. And so you know which way to go. Okay, so and then you do it again. Let's say you get the answer that's greater than. You do the next median, the interquartile range, basically, Q3, and you do it again. And notice that I've made 2 cuts. And so let's just suppose it's underneath. Now I have that final question, greater than or less than 5.5, and I now know the answer of the element that I'm interrogating. I've had to ask 3 questions to interrogate this particular element, which, if you've ever seen that old movie, The Prisoner, is number 6. That's funny. All right. So that's the Shannon entropy. Now I want to teach you another way of understanding entropy, because as we established that the entropy, I'm just going to write log from now on. It's the log base 2 of n, but suppose you have the probability that something equals the one you've acquired. So again, you are in, I want to just describe the action. You are interrogating or testing the subject at hand. Okay. So suppose you have the probability. This is the key idea here, is that you've been given a probability. So it turns out that if, just so you guys, just so you all understand it, if you have a set size of n, then the probability you have one element, one particular element, is the reciprocal of that 1 over n. And so if you flip, it's just a property of exponents that this is equal to the negative of the log of 1 over n. And so therefore, the Shannon entropy is the negative of the log of the probability of any event occurring. So if you have if you know instead the particular probability of an event occurring, then the entropy of the total system, therefore, can be calculated in reverse by taking the negative logarithm of the probability. So that's like a backdoor method to calculate the entropy. And of course, I'll draw it just because I want to be clear, because I know you're writing down what's on my screen. It's the log base 2, again, because we're asking true false questions now. And I'll put entropy 2 as well, because it's a measure 2 entropy. I could instead have a set of tests that measure a different number of questions each time, and that might be a better way of sorting. So that's a separate question, but I'm just going to work with Shannon entropy because it's a gold standard term that cuts across all uses of entropy, whether it's from information theory and data science, probability, statistics, or just the study of heat. Typically, they're working with either base 2 or the natural logarithm, which is not that hard to convert. It would just be the natural log of the probability over the natural log of 2. So that's by the change of base theorem. The natural log of 2, by the way, is, what is it? ln of 2. That's equal to 1 minus a half plus a third minus a fourth plus a fifth. And that goes on, whatever, to arbitrary length. If you let that go on and on and on, and it's something known as eta of 2. I'm sorry, eta of 1. Excuse me. And this is a function that is related to zeta, to the zeta function. I'll just put eta to the zeta function, which is something that there's like $1 million prize if you solve. It's involved with this thing called the Riemann hypothesis. But if you study prime numbers, what you understand, by the way, is that the probability that a particular number is prime is equal to 1 out of the count of all the primes up to that number is typically proportional to the logarithm of x, or to the natural log of x. So that's where you see the prime density function, which you then integrate over, to get the area underneath that curve, which is the accumulated number of prime numbers. And so the question of whether or not this thing is, it's certainly not equal to it, but is it asymptotic or approximately equal to the number of primes, up to a given number, or pi of x is what it's called. That's something that I've studied. So that's why I am sort of able to comment on the entropy side of things, because you wind up studying entropy of prime numbers if you're tackling that problem. Okay, so I did the example of how you calculate entropy. Again, it's this basic, it's the basic formula up top here, which I'm going to just highlight again. The entropy. Oops, sorry about the coloring. The entropy is, very simply, you can calculate it. You can calculate it from the yellow box, where you have in the orange or pink coral colored box. You can also calculate the entropy from the probability. And I think that's a very I think that's a very, very important realization, is that the field of, once you have a probability ascertained that you're banking on, you can convert that into entropy. You can understand the size of the entropy. Now, in other words, you can understand the number of true or false questions needed to sort out all the objects, to bubble sort all the objects in the set. Okay, so let's talk about what creates entropy. So now we're going to get even more operational. What creates entropy? And the answer is very simply mix-ups. So suppose you start out with perfect knowledge. So you're kind of like a demigod here, right? So lowercase God with a lowercase g, I guess. Okay, because you know that you have A, then you have B, then you have C, then you have D, then you have E, then you have F, and then you have G, let's say, in your set, in your hand, so to speak. In other words, you're holding them. Well, I don't like to use a set. I like to use it a hand. So in math terms, if you ever encounter what's called set theory, the way to properly understand that is that in a set, you can hold the different elements of the set as cards in your hand. That's how you translate set theory over to probability theory. Okay, so so if you're like the god and you're holding these things in hand, you have everything in perfect order. But then suppose there is a I don't know, let's just say some kind of dissembler, right? And what that dissembler does is the dissembler confuses the distinction between A and B. So now what you have, I'll show you, is A and B turn into just X, X, and then let's just say C joins them. And then we still have D, E, F, and G. And they're staying in their order. But what's happened is that A, B, and C have become confused with one another. In other words, they've been set equal to one another. So some other kind of godlike or or devil-like entity told these 7 cards in my hand, these 7 subjects, you know what, you are all equal now. You're completely equal. I'm setting you all equal to X, where X is just some projection in their mind. So they are now they have now been scrambled in their position potentially, and you don't know. So you are apprehending them. So you spread your light as the demigod, semi all-powerful God, and you capture these 3. And you're now looking at how many true or false questions do I need to ask, or greater than or less than questions, such as what I could ask, were you higher? In other words, were you ranked lower in the alphabet than B? Could be my first question. And if that's a negative, right, then I know it's either going to be B or C that I'm talking to, and B is holding his tongue. And then I could ask, were you? That's the second question. Were you ranked lower than C? And of course, only C says no, because C is not ranked lower than itself. C is its own rank. So I got there with 2 basic questions. Now, if I had just wanted to get a sense of what was going to be the size of that question process, in other words, how many questions was I going to need to ask at the outset in the bubble sort algorithm? It's log base 2 of the 3 elements. And log base 2, you could calculate that as the natural log of 3 divided by the natural log of 2 is another way of doing that one. And I don't know what that is, but it's going to be something like 1 point. It's going to be something like maybe like a 1.6 kind of deal. Something like that, 1.6-ish. Sorry about that. Cool. All right, so essentially, you know that the 1.6, by the way, tells you, okay, I'm going to need to ask 2 questions, but there's a good probability, by the way, that I might get there, in just in 1.6 or so questions. And in fact, what you can do is you can use this information to kind of optimize the number of multiple choice questions, which would be changing the base. So let's say you had a value of, I'm just going off here. This is kind of what I always do. Let's say you got a value that's like 1.60207 or something like that. And it's some crazy weird logarithm number calculation, right? Well, this is approximately equal to 8/5, you know, or no, sorry, that's approximately, we could just say 16/10, right? And so now what we have is we might instead want to convert this to log base 10, you know, and then of the 16/10, that's going to be the log base 10 of 16/10, and then you can use a bunch of logarithm rules to basically turn this into the log base 10 of 16, and then you just subtract 1 from the final result. Maybe that's an easier calculation to do. Maybe your machines are set up to do a log base 10. But also, I think also if you could somehow get the denominator of the base to match up with the numerator of the fraction, I think that also produces interesting results that can be used in optimizing. So I'll explore that some other time. But let's just put it this way. If you get an entropy value or a number of questions value between 0 and 1, or between two numbers, try changing the base, try changing the number of multiple choice questions, because you will get a different value for that particular type of entropy. So entropy is a base dependent process. It depends on the number of multiple choice questions you're asking. Entropy base 7 might be useful, or, you know, since sliding scales that people so yeah, now let's also look at like this idea of what is perfect order. Let's just use the equation on this one. So the entropy that's going to be found in perfect order, what's the probability, if you have a perfectly ordered system, what is the probability that you're going to find what you want? Well, it would be 100% or 1. So what's the log base 2 of 1? It's equal to 0. So therefore, in a perfectly ordered system, there is 0 entropy. Okay, because you don't need to ask any questions. However, this doesn't mean it's alive. It doesn't mean it's alive, because empty space can have 0 entropy. And this is where I want to talk about something where, again, what creates entropy is mix-ups, right? So the best way to think about this is mix-ups are basically heat in the physical world. So, you know, the temperature as a measure scientifically, it's equal to the average kinetic energy, you know, per, you know, it's like per unit number of atoms, you know, and everything, of course, in chemistry is like, in terms of these things called moles, they're just collections of atoms of a certain size, where they're normalizing the collection size to collections of size that are hydrogen, that are 1 gram. So a gram of hydrogen is a mole of hydrogen, but then you can convert the other elements based on that ratio. And mole is like short for molecule, so it's like a meta collection of molecules. Mix-ups that happen as a result of heat, think about a scrambled egg, right? So when you make scrambled eggs, let's talk about heat and mix-ups, okay? Because both drive entropy upward. So first example I want to talk with you about is scrambled eggs, right? So entropy with regards to eggs. Then we're going to talk about entropy with regards to a signal, let's just say sent in wartime, some kind of like Enigma machine thing. And then lastly, we're going to think about entropy in a person and then entropy in a civilization. So I'm going to just bust out the whiteboard here. Try to get these things more organized. Appreciate your patience, by the way. I'm going to get an editor on this. I have a very good friend and former student who's going to be editing this for me. Okay, so essentially what entropy is measuring, I want to frame it a little bit differently. Entropy is measuring from a state of perfect order how much information you have lost, which is how many questions to ask you have gained. So it's kind of like, it's a measure of work to do. It's the number of work to do. It's how many questions you're going to have to answer based upon and another example of this might be that like you're cleaning your kid's room and you're asking your child, where does this go? Because your wife, child's mother wants this object to be put away here and there. And so the child's trying to explain to you where things are going and you're the one asking the question. So you're experiencing that entropy, that entropic process, except you're providing negentropy, which is you're trying to help put things back in order and then eventually help the child put them back in order themselves. And then the negentropy is sort of captured. And we'll talk about that. So let's look at the basic example of scrambled eggs. So in the case of eggs, right, the state of perfect order is going to produce a chicken, right? So that's its sort of its entelechy, if you will, is it's going to become a chicken, right? But this is not useful to us as humans, mostly due to salmonella. I've definitely had raw eggs. So if you're like a raw egg enthusiast, like I'm not hating on it. I'm just saying most people who don't have super highly robust immune systems and are also not getting super fresh quality eggs, they're going to have a salmonella issue. So that's the idea. So I'm just going to put these in little bullets. So we cook it. The heat scrambles the information. So all of that functional information in the yolk and in the albumin of the egg, and including the DNA material, which is invisible to the naked eye within the egg, unless it's maybe you see a fertilized egg, right? But all of that information gets destroyed in the heat because the heat is taking the egg and just putting more energy in than the current system can possibly filter into a state that continues or persists itself. So the metabolism within the egg, which was in stasis in the fridge, but it's still a metabolic object. It can ferment or commence rotting at any time at some point, and it can receive inputs, even though the shell is pretty good protective layer. If you're looking at what is cooking, essentially, you're making the molecules become identified with one another. So the proteins get catalyzed; they get broken apart into smaller proteins. The sugars get broken down into simpler sugars. These simpler sugars have lost the complexity and the intricacy that they had. So that information was lost in the heating. And all the heat is doing is just taking the cards that you had in your hand and just flipping them over and moving them around and turning it into a probability experiment. And the longer the heat is going on, the more the mixing up is occurring. Temperature is a measure of how much mixing up is occurring at a local region. So if you say that stove is hot, you're really saying it has a high temperature. That means that if you put your hand on it, way too much information is going to be lost in your hand, if you catch my drift. So you don't want per unit time, that is, per unit time. That's the temperature thing. It's a velocity. It's a measure of the jiggling velocity. Whereas the heat itself is more like a measurement of the total mass of information that can be scrambled if exposed to it. So at a certain point, just as the heat will eventually radiate out into the atmosphere, that radiation of the heat out into the atmosphere is taking the metallic atoms that are holding the heat in the stove, and then you have the electron fields moving around these atoms that are experiencing all of this heat, and it's scrambling up their jiggling by changing their electron orbitals. Well, when the heat gets transferred to the atmosphere, it becomes just absorbed by the molecules in the surrounding atmosphere, and then they start to move around and collide with one another. So maybe there's a slight increase in the pressure of the room, and there's a slight increase in the temperature of the room as well, because now the molecules themselves in the room are jiggling a little bit faster. But eventually they form an equilibrium according to Newton's law of cooling. And that equilibrium sets in, and now your kitchen is 2 degrees warmer, but your oven is cooled to room temperature, and your brownies are done. You know what I mean? So, or your chicken or your pot roast is now completely done. So, so that's what we're doing when we're cooking, is we're essentially we're killing the bacteria. Obviously, that's the purpose of the cooking. But in the process, we are breaking down things into their smaller states. Now, that's why I think the raw eggs, raw meat, or as rare as possible, tends to mean that there is a higher complexity to the material that you're eating. But you have to also off balance that against the health of your stomach and like what kind of bacteria you can tolerate. So for me, I can tolerate quite a lot because I don't get sick that often. So I got a pretty robust immune system. So I tend to eat my meat more on the rare side, but it's just weighing the pros and cons. But the amazing thing that I want to talk about is why is it that your eggs, when you scramble them, you've destroyed the information in them. How does that information then become part of you? It's not merely energy that you need to function. You actually need to synthesize new molecules in processes that your proteins have been coded to be able to do the work for. And that is where we get into the topic of negentropy, which is accumulated defense against entropy. So I'll talk about that now. Cool. All right. All right. So what is negentropy? So here's a hint. It's health and wealth. Here's a better hint. It's accumulated, deployable, automated reordering systems. So we got that. Oops, sorry about that. So we got that great word in there, systems, that you hear all the time. If you're into natural law, systematizing, excuse me, that are still functioning, of course, because any system that's complex or complicated can be damaged in various ways. But yeah, accumulated, deployable, automated reordering systems still functioning. In other words, all of that kind of in a nutshell might fall under the word adaptability. So it's a store of adaptability, or it's an adaptability is just the ability to defeat the Red Queen. It's the ability to get ahead of entropy and get as many steps ahead of entropy as you possibly can. So the more steps ahead you are of entropy, let's say in your body, your health is bigger. And the more steps ahead of entropy you are in your community, and then all the political regimes or membership associations that you are a part of in your extended community or your polity or your region of the world, that's your wealth, so to speak. So so that's what negentropy basically is. And this is really interesting because you know, I want to just make a note here. Whereas, oh, sorry, I should do it down here. this is an important note. Zero entropy is perfect order, right? But negentropy is life. What is life? I mean, it's a thing that self-persists, right? So life persists and then also replicates. Actually, I should just say reproduces. Also replicates. And in order to do that, there has to be a bunch of fully functional automated reordering systems that are still functioning. And because we're dealing with, the weather, right? Think about the weather, what's the word? Kaleidic is the word that Kurt used. We have a kaleidic universe. There's so many things to have to adapt to because there are so many extreme energy gradients that anything navigating that's an animated thing on this earth, or even a solid thing on this earth, has to survive. If you're a rock, you might have to survive the oceans or your local volcano. Negentropy essentially could be thought of, it maybe is not equivalent to life, but life certainly has the property that of being able to store its own forms of negentropy. And I want to get into what those forms are, but it basically comes down to you have to be able to, it's the ability to reorder, and it's also the ability to reproduce. And what happens is that these two things, I'll put it down here, are kind of like their own specialty. A person who is reordering things at any scale is going to be kind of going in a different direction with their choices and their time than someone who is rather trying to reproduce what already exists. The reordering what already exists is not going to produce the status quo. It's going to, and it's also going to force adaptability. So this direction, I'm gonna basically call naturally selective. This is a naturally selective or negentropic adaptable to weather change. Actually, negentropic accumulation. Let me just put this up here. And then you're going to have down here preservationist, which would be negentropy against adaptation, seen as entropy. So that makes sense. What I'm doing there, maybe I should just use a colon. By the way, you got to use this select function in Zoom, and you got to tap on a text box and then double click it to be able to get in there. That's the way you do that. So reproduction, I put under just this this term of mass and inertia. Essentially, when an object has mass, all the light energy that's hitting it, that contains the potential to scramble any of the information in the object, the mass essentially keeps the object in the same place. So there's no spatial entropy created, and therefore also no energy observed, and therefore no probability that anything is going to change. So the higher the mass of an object, the lower the probability it is if any random object hits it, that it's going to change. Think about mass in that way. Mass is not Don't think of mass in terms of an ideal type. Think of mass competitively. Mass is just the resistance to a strike that would test for how much mass it even is, right? That's how we test mass. So we measure strikes in terms of momentum and mass, but we also measure mass in terms of momentum and strikes. So you have to see the functional relationship. So yeah, so I also want to bring this up from the previous slide, that there's the Dyson idea, okay, of the enzymatic catalytic efficiency of 54x is sufficient for a reproducing but non-genetic replicating life blob form thing. I know that sounds a little bit vague, that last terminology there, but the basic idea that I'm working with, or that Dyson was working with, is he thought, because he's a genius mathematician, Freeman Dyson, he thought that solving for the question of the origin of life was too difficult to stretch when you had DNA and the various processes that DNA is involved in the cell. And this is because, by the way, now I would understand it through Kurt's work, that DNA is the memory function. So in other words, DNA is essentially a mass of accumulated time, right? Because DNA is the material form of adaptation that you have. Whereas, up here, the naturally selective, this would be more like the mitochondria, which is, it's like needed by all. The DNA is like held by all, and it kind of limits what you can become, but at the same time, it preserves you from becoming worse than that. So, Dyson's idea was that let's just subtract DNA, which is the memory component of cellular life, and let's also subtract the mitochondria, or any kind of notion of organelles or enclosed tissues. Let's instead look at life as a series of objects that are undergoing chemical reactions in some sort of space. The space we are hoping is going to be a changing space. Let me kind of write this out. Actually, so you would need, in the Dyson idea, by the way, I'll just type this down here. In the Dyson hypothesis, you would maybe need some amino acids to have been formed, and definitely some proteins. You definitely would need maybe some, specifically to the enzymes, other catalyze, you might say other reaction catalysts. Got to go from notes here. Right. The enzymes, by the way, are doing, so the proteins do, just so you guys understand this, the proteins do mechanical work. The enzymes are specialized to doing chemical work, as are the other reaction catalysts. The idea here is that these are the components, and then there's also just raw materials. One last thing. Let's just say the sugars, carbs, sugars, right? With just that alone, what Dyson was arguing is that you could, if you could get the catalytic ability up to 54x, in other words, you lower the activation energy to 1/54th the size, thereby speeding up the reaction by an order of magnitude of 54 times. With the given energy available, you could achieve a self-reproducing but non-genetically replicating life blob form thing. And the life blob form thing is going to have a changing volume. It's not going to have a defined shape other than its container. So think of it as a liquid form of life that is compatible maybe with higher and complex life forms. You could argue that this is what eventually our lymph system or our fluid system and the matrix of most cells, the gooey parts of our cells, probably evolved from some network that was like this. And the assembly of large-scale phospholipid bilayer cells probably occurred later on in the process of the formation of life. And this actually is consistent with historical data about the Precambrian explosion, because the adoption of the cell wall in plants was took, I think, about 600 million years before we started seeing evidence for it. So I think that's a really fascinating idea of Dyson's. But essentially, Dyson's idea, I put it all in blue because the part of life that has to do with preserving itself, a self-preserving chemical reaction, is necessarily adaptive, let's say, to changing weather conditions. But you're still not harnessing the value of the memory that's being accumulated. So the natural selection of the genes, really, I should have put up above. So I probably got that wrong down here. Maybe I put that up here, but I still want it to be a kind of blue within the red, if you will. And also this mass or inertia, you know, the preservationist, all of this, there has to also be in here some kind of fire, some kind of other fire or energy. And usually it's going to be some form of light energy, heat energy, could be electrical energy. Typically we want electrical or light. We don't want heat. Heat is really just introducing mix-ups into an environment. So what we're basically presupposing is that, how did the elements get together in some tide pool somewhere on Earth where there was a lightning strike or a bunch of lightning storms at a certain time, blah, 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 in the early Earth atmosphere? We don't know. Could there have been more lightning storms early on in the atmosphere? I think so. The oxygen content was lower, right? So oxygen would tend to absorb electrons. So if the oxygen content was much lower and the carbon dioxide content was much higher, and there was also a carbon component on the ground, which there was, because carbon is an abundant element, you're going to have tons of electrically conductive material on the Earth's surface, because carbon or graphene, if it's not just compressed in a coal or hypercompressed into a diamond, it's largely going to form an electrically conductive surface. You can even see this with a charcoal pencil. You can draw with a charcoal or a graphite pencil and then run a battery circuit on it, just small voltage, but you can get a voltage potential and get an LED light to light up just by using pencils. So the carbon is electrically conductive, and also any storms in the upper atmosphere are going to want to ground. So there's enough carbon in the atmosphere and enough carbon in the ground for conductivity to happen before the onset of a high oxygen atmosphere, which I think would tend to limit, and a high moisture atmosphere, which I think would tend to limit lightning storms, because also the introduction of electrical energy to water in the atmosphere is going to separate the hydrogen into the water into hydrogen and oxygen, and to a certain degree into ozone. So yeah, oxygen-rich atmosphere just creates an ozone layer when you have a lightning storm. But if you don't have an oxygen-rich atmosphere, you don't develop any ozone in the upper atmosphere. So before we had life, spitting out oxygen as a waste product, we didn't have an oxygen-heavy atmosphere to create an ozone layer. That changed the game, right? Because the UV rays now hitting the ground are going to be different and shielded. That's kind of like a cell wall protecting whatever life is already kind of in the system. So that also might have been happening at around 600 AD, that enough photosynthetic plant life around 600 million years after the onset of life, maybe enough accumulated goopy algae-like plant life has been just farting enough oxygen into the upper atmosphere that the ozone layer formed. And I don't know if we could test for that geologically for rock exposure to radioactive ozone isotopes. It's hard, I think, to get oxygen isotopes that are radioactive. But anyways, I'm just imagining a situation where the ozone layer forms at or a little bit after the Precambrian explosion. And what that kind of does is that takes whatever DNA or RNA or replicator architecture exists at the time and sort of solidifies it into place, or solidifies the conditions for it to stop randomly mutating as a result of being exposed to UV light. Because it's been shown that RNA will increase its mutation rate when exposed to a higher UV rate. So in the Dyson hypothesis, in a sense, this early metabolism also could be like a form of cancer to us, right? So if we descend back into that just pure state of metabolism, that also could just be us descending into a kind of cancer. And also the thing to understand is that the cancer is undergoing its own catalytic process and enzymatic process that's furthering itself, but it also seems to be associated with low oxygen or oxygen deprivation. So it would make sense in Dyson's hypothesis. He said that modern living systems have well over 100x. Most enzymes today have well over 100x. This is Dyson again. Speed up, but 54x is the minimum required. And I think the reason it's 54 is that it's approximately 54x. And I think it's I believe actually the reason is that it's equal to e to the fourth. I think it's like e to the fourth power. Is that right? Yeah. Which is approximately. So that just tells you it was the solution to a set of differential equations. And every time you have differential equations with tons of e constants, right? The letter e, whatever e, well, I don't want to talk about e in this video and what it is. I could give all kinds of whatever, but really what it is it's combinatorically interesting. In fact, it's the most combinatorically interesting number for the study of smooth manifolds or motion in surfaces that change smoothly, calculus friendly. And the technical term for those functions are called C infinity functions, but math lesson. Anytime you're dealing with a C infinity function, you're going to see exponentials in the in any kind of process. Exponentials also get used all the time in robotic languaging for how to move a robotic arm. So I'll make another video on that, how the best way to understand robotic kinematics and also reverse kinematics. Not only what are the steps necessary to grab an object, but if an object is here, how do you calculate in reverse what steps your robot fixed at this location over here has to do? So the kinematics and the inverse kinematics for robots can actually be expressed very beautifully in this language called the Clifford algebra, which uses exponentials all the time. So that's something we'll maybe talk about in another video with physics and robotics. Cool. So I want to just close this side here, which is that like the gains in negentropy, E plus, right? From what I can see, there are geometric gains that you can gain, right? So locality or connectedness, right? But also partitioning and proportionality. Geometry has all of those aspects to it, right? So if you want to capture a lot of what's kind of, in a sense, part of what Plato would call the good, he would say study geometry. But there's also, I don't know if Plato liked working, but look how I'll just whoops, that was funny. Let's do this. Partitioning, which is when you partition something, you're dividing it into pieces. Or sorry, that's just subtraction. Whereas literally to subtract means to partition out, but then proportionality, and that's division. Locality, connectedness. I don't like to associate that with addition, but it's just associated with translation. So really, you could kind of think of it as like positive and negative, but it's really just motion, translation. There are places you can go. and work is product. Which is just energy directed against a gradient, which itself cool. That's a product. So it's literally a multiplication sign. It's being productive, it's working. That's force times distance per unit movement. Then there's also power, which is work over unit time. So that's kind of like your work capacity. And then lastly, you have genetic, which is memory. And what memory does is memory allows us to play that bubble sort game, not for ourselves, but to get the results of other people doing the bubble sorting for us. Now, if you, I'll show you a graph right now that's gonna kind of illustrate the efficiency of the bubble sorting algorithm. All right, so what I have up here is I'm in Desmos.com, and I've got a graph that I'll just, I don't even have to title it, but it's basically a graph of how entropy scales with number of objects. So if for instance, you have a set with, let's say, 8 objects, like we had earlier, you can see that that's, if 8 objects is your input, then the entropy would be your output, which is 3. So the y coordinate here is just giving you the output. And if you were to get to, like, let's say 16 objects in size, the entropy, or the number of true or false questions needed to bubble sort that algorithm, or to bubble sort your way to that answer, is 4. So that's basically, you can see that it's not hyper efficient, or how do I put it this way? No, I take it back. What I got lost in my next thought. What you can see here is that as your set size gets way bigger. So what I'm going to do here is I'm going to kind of zoom this out to make the x-axis, start with set sizes of 0 and maybe conclude somewhere around set sizes of, let's say 10,000. So what you can see here is that, gosh, I mean, most of the gains in entropy come, graphically speaking, from like the first, I don't know, 1/10 of the graph. And then the next, set of gains, it's kind of like it's getting flatter and flatter, this curve, as you can see. So, even when you have something like 8,000 objects in study, the number of true and false questions that you would need to sort them is still only about 13. In fact, 2 to the 13th power is equal to 8,100 and what was it? 90. Is that right? There's something off there, but it's probably a rounding error. I think it's 8192, not 8190. But yeah, it's power of 2. So anyways, you could see, though, also what happens, that if you increase the number of multiple choice questions on your test, you can see that this significantly lowers also the entropy curve. Now, of course, you're still performing more steps, right? So if if I wanted to instead look at what happens in terms of the total number of steps, so the number of questions times the number of states per question, this would be b times log of x. Let me just zoom out a tiny bit here. This is really this is now the total amount of steps, or total amount of work that you must do But if I increase my base, you can see that what's happening is that at first there's a reduction as you get closer to the base of E, and then there's a minimum, and then there's an increase in the amount of work that's done. So it turns out that in base E, if you're actually sorting in that weird irrational number E in and around that base, you are going to be doing the minimum amount of work that's necessary. And that really doesn't apply to what we're dealing with right now, but in terms of large scale probability statistical measures, and also in terms of physics and in terms of aggregations of gases, that does matter a lot. But no, what I'm trying to do is look at the cellular level at like a white blood cell, for example, and just try to understand how is, let me just write this down. How is the health of a body, which I'm claiming is negentropy. I'm not claiming that life is negentropy. I think it has something to do with negentropy, but health is certainly negentropy, different stores of negentropy. So how is the health of a body accumulated? Well, you increase the number of anti-mixer-ups, right? You produce new unadulterated versions of what proteins you need. DNA, you know, DNA right there, you know, is going to code for RNA, which then goes through the whole process for mRNA, whatever. I could actually just condense this, and then you just get the protein, the DNA, and then there's some sort of work or action that is performed. By the way, I want to define work and action formally again. Work is equal to this, and then and power is equal to the partial derivative of work with respect to time. And then I also want to put this down that there is also the action, and that is equal to the kinetic energy minus the potential energy. So this maximizes energy allocated to kinetic, minimizes while the potential energy can vary depending on what most increases the kinetic energy. So in other words, by this idea of action, right, in physics, objects pursue what's called a path of least action, and that's what that concept of the path of least action is how all of the different quantum physics, quantum field theories are based upon that formulation of Lagrange, which is the integral, the action, you know, formally speaking, is really it's the integral of the kinetic energy minus the potential energy on a path along X. So you basically, what you can do is you can reformulate all of Newton's laws in terms of that integral, where if you do a bunch of mathematical algebraic stuff called integration by parts, if you learn that in AP calculus class, but if you do integration by parts and get clever with what initial values you plug into the differential equation that you get when you integrate kinetic energy and potential energy, you get this quantity called the action, that when the action is equal to 0, you get Newton's laws in an inertial frame of reference. You get force equals mass times acceleration, or, mx double dot, equals force, right? So you basically get that from integration by parts. You actually get it. You have to do what's called calculus of variations. It's just a bit of reasoning and analysis that you can do with differentials. But this path of least action in quantum physics, it doesn't establish which path the object will travel. It simply establishes the probability that an object will travel along that path. So that's how the path of least action was adapted to quantum physics. It's no longer calculating the deterministic Newtonian path of least action, Lagrangian path of least action. It's determining a path of particular probability. So, but in either case, the idea is that you want to maximize action against a collidic universe, because if you can increase your store of action, then you can ride that gradient. You have more paths of lower action that you can go down in meat space. So essentially, the health of a body is accumulated. The answer is in logarithmic time, because it's all bubble sorting. In, out, right? Kill, in, out, or it might be base 3, right? Because it's like there's ternary logic. So it might all just be a curve, in base 3. For some reason, I lost my Desmos privileges here. There we go. Right, so it would be this curve. It's not that much different than in base E. So whether you're doing Shannon entropy, base 2, maybe you have a ternary logic entropy, base 3, or you're doing base E because you want you want to be dealing in spaces that are really nice with calculus. Doesn't really matter, plus or minus a factor. Cool. So I just wanted you to see that graph, that when you do, you can add more and more and more entries, and the bubble sorting algorithm only has to make a small number of new decisions. Now, the time that it takes to scan that number of entries, I'm not factoring that in, okay? So the velocity it takes to move through the hard drive. So it doesn't work out that you just completely don't have entropy gains. You do have entropy gains, but it's probably going to be something that, curves, trying to see if I can get the grid lines to be rectified. But I want to get that B out of there. Yeah, something like that. So it can look, I think that's linear. Yeah, that's somewhat linear. It's almost linear, but it's really x log x, x times log of x. Slightly worse than linear. So I'll stop this. All right. So it's time to do some real math, huh? So here's the basic question, and I'll walk through it. I got my coffee, by the way, because if you're doing math, you've got to have some coffee. But what is a logarithm? Like, what the heck is a logarithm? What's the deal? Oh no. All right, so I got it all fixed. So yeah, so if I'm looking at like what is basically a logarithm? Well, the natural logarithm of x, right, has a special definition. It's this integral. It's this area underneath the curve 1 over x. So if you were to graph in Desmos the graph of 1 divided by x, it's like a hyperbola. It never quite hits the x-axis. Well, if you accumulate area underneath that between the numbers 1 and x, the accumulated area is called the natural logarithm of x. Another definition that's maybe more generalized, but is going to confuse some people, but I'll just put it out there for the real math nerds. It's the inverse of an exponential, and especially a Lie algebra, which is any kind of algebra that allows you to convert. I have this down here to convert a fraction of a path or the interval translations on the interval 0, 1, and to turn them into scale factors. So it's summarized down here that logs will turn multipliers into adders, basically, and it will turn exponential functions into translative. Exponentials turn translations into scale factors. So if you think of a translation as a logarithm, then an exponential will take that translation and map it or send it to the corresponding multiplying factor. So, I think if you understand the properties of a logarithm, right, e to the ln of x is just x. That just means that the multiplier corresponding to a translation of ln of x is just the multiplier of 1 times x, basically. So I also like to think of it as an accumulation of probabilities, and that's going to motivate this next understanding of the logarithm over here, which is that it's often sometimes good to try to understand the meaning of an integral in terms of an average. So don't think of just this integral or this area, but take that area and then divide it by the length of x, basically. And it turns out that if you do that, if you take the natural logarithm and you divide it by the length of the interval x, you basically get what's called the probability that a randomly chosen number is prime. So therefore, the inverse of this, or raising this to the -1 power, or raising both sides to the -1 power, gives you something called the prime counting function. And if you can prove, by the way, that the error in this equation right here is sufficiently low, if you can prove that it's basically something like a constant, the order of the error of these two things is something like 1 over the square root of x, then basically, in other words, something involving prime probabilities has to be off by about 1 out of the square root of x of the sample size set. So so I'm kind of working on that one. But if you solve that connection, if you can figure out how to prove that that bounded gap, then you've essentially proven the Riemann hypothesis, and then you can collect $1 million check. It's kind of funny. So yeah, so basically though, like the thing that I wanted to convey here is that a logarithm, which of course measures entropy, it also counts digits. It also seems to be involved in the counting of primes, right? And so essentially it's some kind of a counter. It counts the number of viable states. And what I'm arguing here is that it's a measure of the entropy that accumulates, or conversely, the negentropy, or the barriers to entropy that you accumulate. So another way of thinking of it is that as long as you're accumulating, I'll go to the next slide here. As long as you are accumulating negentropy at a rate that's faster than some logarithmic function of the number of states, of the number of participants, you're going to be fine. You're going to be beating the red queen. And then the question, of course, becomes like, how much do you want to beat the red queen, right? Do you want to go for the maximum adaptive velocity possible? Do you want to go for the maximum amount of negentropy possible? Unfortunately, it's not quite as linear as I would like to make it personally, but I do want to float this idea that what life is, or I'll pause that. I don't know if I can define what life is, but health in any subset of life appears to me to be the negentropy maximized per unit surface area. In other words, surface areas will transform to maximize negentropy in any naturally selected species. You would have to say that it actually has to transform at a rate faster than the logarithm. Not that I want to get into this right now, but if you take if you maximize, if you can basically create a two-dimensional surface that almost manages to fill three-dimensional space with all of its foldings. Think of like an aluminum foil ball that you fold up into a lot of different micro folds, or kind of like the way the brain is a bunch of little folds. The surface area carries the information, essentially. The negentropy, therefore, it makes sense in our bodies that our bodies try to maximize the amount of surface inside of our unit surface area. So what you have is this notion of interior surface area, which is maximized by all the little folds that we have inside. And those folds, by passing ingredients or fluids through a barrier, perform some kind of sortition. And they have to do this at a rate that's faster than the natural log, than some function of time less than or equal, bigger than or equal to the natural logarithm. Or sorry, the logarithm, I think it's the natural logarithm. I was thinking the logarithm base 2, but it was probably the natural logarithm you have to beat the Red Queen. But it's the surface area that carries the entropy of a shape. Very important here, you know, Stephen Hawking got into an argument with another physicist. I think his name was like Jacob Berzelius or something. But Berzelius won the bet, which is that entropy in a black hole, which I'm not sure I necessarily believe in, but I'll get onto that in a future slide. I'm cheerily doubtful in black holes, but I'm not convinced that there can't be one. But it wouldn't necessarily be what people think it is, like some sort of a wormhole. It would just be a very, very, very dense compacted ball where the amount of work required to make anything happen is so great that you can't perform that work, and so therefore there is no time at the singularity, because everything is basically burned to a crisp and then neutron star compacted together in a kind of never ending, but still never. You can imagine that things keep compacting, but that they never quite go to zero. You know, it's not like it's one point. It's a mass. It's a ball. It's a star-sized shape that is adding size, but also compacting its size because of the gravity is finding is breaking new barriers involved in some kind of an internuclear forces. Not to go off on a tangent there. But the surface area determines the entropy. So I'll switch colors here. You know, what is this concept of surface area at the political or the interhuman scale? And I'm arguing, and I think Kurt, you argue this too, it's reciprocity in markets provides the maximum negentropy possible, or the maximum number of positive resorts possible in a given time or space. So in other words, if entropy is a process of unsorting at about the rate of bubble sort, right? Two objects that were here get switched and get juxtaposed. You could say that it's log base 2, log base 3, log base 5. It doesn't matter in terms of the base. There's some base, maybe it's the natural logarithm, doesn't have to be, where things are unsorting. I know in physics it's the natural logarithm, that's what's used, but then it's also, there's a constant factor in there. So it's really a logarithm to some sort of base involving the surface area of a unit sphere, or some sort of unit ball of size of density normalized to 1, something like that. I don't know what it is, but the point here is that there's some logarithmic base that is the rate at which stuff in general in your region of the universe is unsorting its orders. So wherever the air molecules are it's very windy today, there's trade winds coming through in Hawaii. So wherever the air molecules happen to be at moment X or moment T, then at T+1, one increment later, right? How many sortitions, bubble sorts basically occurred to get those air molecules to switch ordinal position, not their cardinal position. Don't think of it as having like particles having a coordinate X, Y, Z. No. Think of it instead as that the particles are switching their order against one another. right? Because if all the particles move together in relative to some other thing, there's no entropy increase. It's only when the particles mix up that there's an entropy increase. So yeah, so what I'm trying to do with this model right here is I'm showing how, imagine a kind of a sphere, and it could be a multi-dimensional sphere that you can move in, meaning that you just have n choices of motion in any given time. There's 3 choices of motion in space, but there's also choices of motion with each of your hands and your feet. So you really have, it's a multi-dimensional set of choices. It's not like, something that you can geometrically visualize. But if we could put all the choices inside of a geometric shape, imagine that being this interior ball right in here. And you can navigate inside that ball of all the beings that are, tasked with the job of mass reproduction. They're navigating via positiva. And they're basically being shielded on some level from natural selection, from entropy. So in other words, you have entropy, just kind of coming in at the frontier, and this entropy is coming in, and it's the devil. It's bedeviling. It's just moving everything around. It's taking this and moving it here, or it's taking these 2 things and making them think that they're equal. Exchange their heat, exchange their energy until no more work is capable. Right? That's what equality does. Is it creates equal amount of energy in each location, which means there's no differential in energy, which means no work is possible between them. So it's like the trivial form of reciprocity. Nothing's happening, and we have perfect reciprocity. So you can think of equality as actually, it is a form of reciprocity. It's the trivial form of reciprocity. I digress. It's the lower dimensional form of reciprocity. In other words, you can think of it as the bias term in a statistical analysis or Fourier analysis, but who cares? I know I'm right, but I don't want to prove it right now. So you can think of markets as being the next layer that surrounds this society. So you have society, which is kind of in here, navigating via positiva. And then surrounding that, you have the world of markets. And then surrounding that, you have the world of frontiers, which I would say the military is for sure involved in the frontier, geopolitical advantage, even just military just means geopolitical advantage, right? Using that to your best advantage becomes your military, becomes your first, it becomes your first line of defense institution, basically. Now, of course, even if your army takes a hit, your markets might still be resilient to a certain degree inside. But of course, if your army totally takes a hit, then entropy just comes in like gamma radiation, fries you, okay? So what life is everything inside, these markets where humans are interacting with frontiers. And this military layer is, just this very thin kind of layer that is surrounding our economy. Of course, it's a surface area of a sphere, but that is the place where adaptivity is that is greatest is required, is both in markets, which is itself a frontier of the entropy. It's responding to the entropy inside. So I'll get to that in just a second. And then you have the military is responding to the entropy sort of outside, or science is trying to make sense or make order of the entropy outside. By the way, when you can take the combinatorics of everything happening outside of your bubble in the universe or your sphere of interest, if you statistically sort of analyze that and you find that it's computationally reducible, that's what we call a science. And so a science is basically the case studies of things that are computationally reducible, either by first principles, they're reducible or deducible, or they're just empirically reducible, that we understand that there's only so many interesting cases and they fall into different clades or lineages or categories. Okay, I know I'm talking about a lot, but so I'm just trying to point that out here, that if you're a living thing, your barrier to entropy, or the amount of negentropy that you can accumulate, what you're trying to do is you're trying to create a barrier outside that minimizes the amount of entropy that you're going to receive from the outside. And the best way to do that, of course, is to become spherical. So humans, even though we're not perfect spheres, we're basically a bunch of attached spheres if you look at us all around, right? There's all these circular arcs that you can kind of see all around the body. And of course, the head is roughly spherical. So we're designed and it's easy for us to curl up into a ball. And most animals can kind of curl up into balls in their own kind of way. They're roughly spherical. They're certainly topologically spherical. If you want to look that up, you know, the genus of the shape, roughly topologically spherical. We have holes in our bodies, but it roughly averages out that we're spherical, and we just perform exchanges through the surface. So the question is, how do you maximize the I'll just put this out here. How could you get the font a little bit bigger, and then I'll end this video after this. How does one, which is a bubble, maximize negentropy with the resources available? Well, it's really simple. If this is your bubble, okay, so what I'm going to show you right here with the red, this is the red queen. So this is, you know what, I'll do this with a nice thick, darn it, I'll try again. That's better. So you can see right here, this outer layer is basically the entropy load being imposed upon the people inside the bubble. Of course, this is graphical representation. In real life, the bubble doesn't have to be a perfect sphere, right? It could just be the sum total of all human beings and their ability to communicate with one another is effectively the data network. But the data network itself, you could do a topological measurement on it and prove that it's either spherical or it's torus shaped, or you can calculate its genus. It could be a Mobius shaped graph, doesn't matter. But let's just assume that it's spherical for the purposes of modeling, because this model can be adapted to whatever shape the data reveals the human action graph that the human action graph says it is. And so basically what you have here is you have the entropy be negative. And so you have to come up with a certain amount of positive entropy. And so you have to maximize sortition on the inside. So it turns out that the solution is trivial, and it's what you kind of already think. Is you got to get busy creating a whole bunch of little nooks and cranny kind of like interlocking surfaces inside, basically, right? Like if you can maximize the amount of layers on the inside and exchanges. So I'm just going to put this here, maximize the markets. If you maximize both the number and the quality of your markets, it's kind of that simple. And now in this case, we're talking about an electrochemical gradient in terms of exchanges. Some chemicals are in kind of a state where they're looking to decompose, and the decomposition can be achieved by cooperating with another molecule. Now, of course, in chemical reactions, there tends to be an arrow of time where entropy is maximized, and that is also what you're also kind of facing, which is that as chemical reactions take place, generally speaking, the disorder or the amount of freedom, so to speak, from oversight of all the different particulate pieces seems to want to maximize across time. So that's kind of funny. So in other words, if you can create negentropy or functional markets on the inside, you can face all of the red queen on the outside. However, you have to also contend with there's a certain amount of intrinsic, which is basically your civilizational heat. You have some people that are maybe performing false exchanges, scams. They're creating things like, I think, for example, colleges and universities become these like walled gardens where the exchange value of what you're receiving is much lower than the perceived intrinsic value. Now, of course, what you are signifying is that you are of a certain intrinsic value. I would say that you can write a decent letter, write a decent paragraph, write an email to a boss, follow a set of written instructions. But unfortunately, for some majors, not even that, right? So, but of course, if you go to college in a STEM field, you're still going to come out with a very rigorous education in terms of your calculations. So, I was an English major and I took the major rigorously personally. I did all the readings and did all the homework. But if I'd had a better professorship at Northwestern, I would have sure completed the math major, which I started first 2 years. I was in an accelerated program called Menu. Oh gosh, that was fun. It was all just like infinite dimensional multi-vector calculus first trimester, and then second trimester, it's like integrating all the linear algebra into that, and then linear algebra course third trimester, and then differential equations in start the second year, differential geometry. What else was there? A whole bunch of like statistics and n dimensions. And then I sort of just fell off. At that point, I just sort of lost interest when it got to proofs, because it began to, I don't know, it just began to wear on me that I wasn't being Leonardo da Vinci. I wasn't using this math and solving real problems with it. Or somehow it was not even that. It was that the subject itself didn't seem concerned with real problems. It seemed concerned with its own internal, how would I put it? Information proliferation, maybe. Work expands to fill the time or the budget provided. So it seemed like math became this language game. And I read all of Lewis Carroll's works, by the way. Charles Dodgson, he had one of his works at the Northwestern Library that was a different work than Lewis Carroll. But Charles Dodgson was the real name of Lewis Carroll, which was a pen name. Lewis Carroll was trying to write against the absurdity of imaginary numbers. And so that was his attempt to satirize them, was Alice in Wonderland satirized the quaternions, and I believe Through the Looking Glass satirized the complex numbers. I might have those reversed though, but one book handles the complex numbers and then the other one handles the quaternions. I know that the episode with the Mad Hatter, where all three people change positions sitting at the table, that's a depiction of of the logic of how quaternions multiply. Something like I times j times k is equal to -1. I think that was the foundational quaternion imaginary equation. But anyways, not to get too long in the tooth, this video is going to get edited, so this is just a draft. But yeah, so if you can maximize, let's say, the number of markets on the inside that are positive, you win and you beat the red queen. But if instead you create all these like self-absorptive markets on the inside that really are just a form of like a waste of attention, it's a waste of time. In other words, you could be building more systems. There's all these different, let's get that ugly thing off, which is the sort of the media empires. That's what all that red intestinal yuck was. But if you, but if you look at, I'll be kind of funny. Let's suppose you're in the middle, you're a little baby, and you got all these little people kind of in the middle. You might have a natural advantage towards one particular frontier. Like I've always had a natural advantage in math. So, I chose that particular, path. But it's, I would say really it's a combination of the intersection of math and epistemology. I've always, essentially a study of lying, but not really lying, but just of hide and seek games in general, why people can't see things. And I think math proofs are interesting because they reveal something you couldn't see before. So there is a psyche-delos or psychedelic component to when you really see a good visual proof. But I chose that direction. I've also really enjoyed computer programming when I've done it for projects that I initiate. So I also could have maybe, chosen that direction, right? So that's maybe like a different direction. But each people, and then another person might be like, okay, I want to get really, really good at, at this and so forth. But what I meant to do was I meant to make this arrow here go in the opposite direction. Let's suppose that instead of me being virtuous, and let me kind of clean this up here. Instead of me being a virtuous kind of guy, um, and pursuing a life as a teacher, tutor, but especially sort of a pedagogue of mathematics, in that I'm helping to uncover the barriers that are hard to see around. And I have to play a sort of game of hide and seek of, why can't my students see this? I have to get inside their head, that's fun. It's a fun use of the human time together. And it's enlightening for sure, because I definitely see my own foibles in them. So I love that aspect of it too, that it keeps me humble. So, but there are some arrows, for example, like this arrow right in here. I'm trying to make it so that it's pointing back in. That's not a career, for example, that's helping people. That's a career that's hurting people. It's consuming. It's kind of like an arrow in the opposite direction. So if for instance, let's just imagine there's another direction over here that I'll put in pink. Let's say you go in the direction, and this direction over here is essentially the direction of you become a mother. And of course, only certain members inside the set go in this motherhood direction. But if you kind of imagine, is there a reverse kind of arrow to mother, or almost like a reverse direction? Think of what that might be, right? But the idea though is that maybe motherhood is a little bit of the purple and also a little bit of the pink. Like maybe in other words, maybe the purple is actually the flirtation, and the pink though is the devotion, right? So maybe if your devotion is bigger than your flirtation, then fundamentally you come out okay in this vector direction or a career choice of motherhood. Anyways, the point I'm trying to get at is that if you go too far, let's say with an inborn talent like to flirt, you're actually creating heat, negative competition in markets on the inside. Whereas the healthy sort of mating markets that have existed in the past, to the degree they were healthy, they actually built layers and layers and layers of defense against the inevitable entropy that people would face across time. So I thought that that's a really interesting reframe, not necessarily of life, but of health. I have right here this little thing I'm squiggling around, and I'll end with this, that I think life is basically a bunch of negentropic cycles. And so the meaning of life, folks, is if you are feeling crazy in your head, or you're noticing something in your head that your friends around you can't notice, that just means you have a time advantage. And so you have a negentropic advantage over them. Now, it's not that you want to have an advantage over your friend, let's say, but it just means that you have, let's say, you've chosen an arrow in which you have a time advantage or a specialization. And it might just be that the best way for women to concentrate their time advantage or their ability to maximize negentropy across time is to unify themselves in kind of like a culture in a direction of motherhood. And I think that's been true in all healthy societies, is that, women can be this way, women can be that way, but as long as the motherhood value system is like very strongly enshrined, and fertility is very strong, like that the population seems to have enough number, at least, to even perform natural selection, right? Because if you don't have number, if you don't have reproduction, you can't even endure natural selection. So the value of the mother, therefore, is very, very high, and all available females who become mothers are maximizing the negentropy of that bubble, or of that tribe, so to speak. Whereas maybe the men, maybe they sort of specialize and pick different areas on the boundary or on the perimeter. So in primitive human societies, it's literally, I'm going to get good with the bow and arrow or with the spear because I can defend the literal perimeter. Others would be like, the perimeter might be the ability to grow food, the ability to find food. But growing food means the amount, you're planting for a future moment in time. So your actions right now are building towards some future date, right? So you're starting to develop more of a sense of the future, but also in a hunt, you would have a conception of a future, maybe a more cyclical conception. Anyways, I could go on and on and on, but I'm just trying to point out kind of in all of this, and you can see, I have all these like physical notes right here, right? That the derivative the time derivative of the logarithm is equal to 1 over t. So in other words, accumulations of reciprocity. I know that sounds kind of mystical and mathematical, but I'm just trying to explain that logarithm is essentially a probability accumulator. I'll go into it in a future video, but you just have to perform sortition faster than some logarithmic curve. So yeah, so I'm just basically kind of saying that, like, I don't know what the conditions for life are, but I don't know if this is a sufficient condition for life, but life is required to perform enough sortition at a rate that's faster than entropy. Now, it might be that an AI system can also do that within its limited domain of materials and media or mediums. But I think it's pretty clear, when you see it, that living biomass just has maximized every unit available of surface area to perform some pivotal key function, or at least to do no harm. So if you look at parts of your face and you're like, oh, is there a particular beauty to this part of the chin? Not really, but it's doing you no harm being designed that way as well. So your negentropy is being, so your entropy, do no harm means that your entropy intake is being minimized, and then do good means that the negentropy that you're accumulating inside is being maximized. So that there you have it, bad and good. So anyways, this is a rough draft, and I hope you like it. I'm honored to make some videos that showcase some of these mathematical analyses. So.